Good afternoon, everyone. Thank you for coming. Over the next few minutes, I'll be presenting our research on CRAID, a data distribution strategy for large-scale RAID arrays that aims to solve the existing problems with upgrading these devices without loss of performance or load balance. First of all, let's begin with a little bit of background. Despite all the recent technological advances in storage technology, RAIDs continue to be one of the basic building blocks for large-scale storage architectures. The main reason for this are that the RAID offers good performance levels due to its parallel data distribution. It also supports reliability mechanisms like parity codes or replication to safeguard users' data, and allows to aggregate the different data spaces of the devices to offer an enlarged storage capacity. In addition, these benefits can be achieved at an acceptable economic cost. Nevertheless, as client requirements increase with time, users usually need more performance or more capacity from the array, and the RAID needs to be upgraded by adding more devices to it. Unfortunately, grading a RAID in such a manner implies significant amounts of data migration between old disks and new disks if we want to be able to use them at their full capacity. The main reason for this is that the upgrade process should be able to produce a uniform data distribution in order to avoid hotspots or device underutilization. Besides that, the upgrade process should use minimal data migration and should be interleaved with normal user operation if we want to be able to support always online 24/7 services. There are already several methods that have tried to solve this problem and already can successfully upgrade RAID arrays with minimal data migration. Nevertheless, depending on the resulting data distribution, some problems can arise at a later time. For instance, the uniformity of the data distribution may degrade after several subsequent upgrades, or the performance scalability of the data distribution may be limited. In addition, if we want to add support for parity computations during the upgrade process, the overhead of the upgrade significantly increases. Thus, rebalancing even an ideal amount of data can be too expensive under some circumstances. This realization led us to the following question. Is it possible to rebalance less than the ideal amount of data and still achieve the performance or the load balance of an ideally redistributed RAID, or at least close to it? In order to answer this question, what we really need to consider is if we really need all data perfectly redistributed. It is often the case that RAID clients don't need to access the whole data set at all times, but rather frequently access a small subsets of data during certain periods of time. These subsets of frequently accessed data, or hot data for short, usually represent only a small percentage when compared to the whole data set and remain stable for relatively long periods of time. In addition, they also focus a large amount of user accesses. Under this situation, it makes sense to assume that if we were able to perfectly rebalance only this hot data in real time, good performance results could be achieved, and the upgrade process would be significantly reduced. In order to test this theory, we designed a data distribution strategy called CRAID that decouples the management of hot data from the management from cold data inside a RAID array. Excuse me. What the CRAID controller does is to create a cache partition for hot data using a small percentage of the capacity of all disks, and using the remaining capacity to create an archive partition where data that is not currently being used will be placed. Once these partitions are created, hot data is identified and tracked and copied directly to the cache partition. When the cache partition is full, the cache partition behaves like a traditional cache in the sense that we only need to evict the colder data and replace it with the newly detected hot blocks. The advantages of this organization are that we can create a larger cache using only a small percentage of capacity for each disk, which means that important data has the opportunity to be cache resident for longer times. In addition, this catch partition is a disk-based catch, which means that any optimizations that we compute for this hot data will be catch resident for longer times and will survive any potential unintended shutdown of the array. This also gives us the opportunity to cluster hot data, which may lead to more sequential data access and reduced seek times. And finally, all these benefits can be achieved using already existing devices, which may avoid the need to purchase additional hardware. The CRAID architecture is based on three main components: the I/O monitor, the mapping cache, and the I/O redirector. The I/O monitor is a component that analyzes user requests to identify hot data and simply schedules the appropriate partitions, the appropriate operations, to transfer data between the different partitions. It's also in charge of choosing which data needs to be replaced when the catch partition is full. In order to do that, our current prototype supports simple cache management algorithms like the least recently used or least frequently used with dynamic aging, because they have shown, in our test, they showed good prediction results, and they can be implemented in a controller, can be easily implemented in a hardware controller. The second component, the mapping cache, is a component in charge of translating user logical block addresses to logical addresses either in the cache partition or on the archive partition. Since this component is going to be accessed in the critical path of user requests, we need lookup to be really fast. And since it will be held in the memory of a hardware controller, we also need its memory footprint to be really small. Our current prototype uses a tree-based structure that guarantees logarithmic lookup time and a memory footprint of about 6 megabytes per gigabyte used of the cache partition. Also, notice that if we were to lose the mapping cache, access to all the data in the cache partition that has been modified would be lost. Therefore, in order to avoid this problem, we also included a log that holds the dirty blocks and their translation so that they can be recovered in the case of a crash. Finally, the I/O redirector is the simpler component of the three that simply intercepts the user requests and sends them to the appropriate partition. Notice that we're using delayed write schema in order to minimize the number of background operations that conflict with normal user operations. The rebalancing itself is performed by the I/O monitor when new devices appear. When this happens, the I/O monitor only needs to identify which blocks have been modified in the cache partition, copy back this data to the archive partition, and invalidate all the contents of the cache. Once the contents of the cache are invalidated, we only need to extend this partition to include the new devices and begin the tracking process anew to fill it with the currently hot working set. The advantages of this kind of rebalancing are that we can begin using new disks as soon as they are added to the system, and we can also create long sequential chains of potentially related blocks. One of the disadvantages is that we are invalidating all the contents of the cache partition, and then that means that all the previous optimizations that we had computed for this set of data will be lost. Now let's go to the evaluation of our current prototype. The evaluation of CRAID is a trace-based simulation that uses the well-known DSIM storage simulator. In the paper, we review seven different traces using different workloads, but here we will only show the web users dataset from the Florida University traces and the project trace from the Microsoft Research Cambridge traces. All the simulations have been run for 1 week of trace time and use arrays of 50 disks plus 5 additional SSDs in some cases. We use an LRU algorithm since in our evaluations showed the best hit and miss ratio trade-off, and in all the simulations the cache partition is called at start. The strategies that we are simulating are an ideal RAID 5 that is completely restriped and uses the 50 disks as a stripe size, an extended RAID 5 that we will call RAID 5 Plus that mimics a real system that began with 10 disks and grew by aggregating subsequent sets of RAID 5s until we reach the 50 disk mark. These two strategies are extended by CRAID by adding cache partition using 50 disks on top of it that we will call CRAID 5 and CRAID 5 Plus. And finally, in order to compare CRAID against dedicated SSD cache, we're also creating two variants that use five dedicated SSDs for caching. Let's begin by reviewing the performance results for read requests. In these figures, the y-axis shows the response time in milliseconds computed as a confidence interval measured during for all the operations in the trace. The x-axis shows different cache partition sizes the strategy was configured with. What we first need to okay. One thing worth mentioning is that the extended RAID 5 in all simulations shows significantly worse results, worse performance than that of the ideally redistributed RAID 5. This is to be expected since the extended RAID 5 stripes are shorter than the ideally redistributed RAID, and the latter shows has a better chance at parallelism than the extended RAID 5. Regarding the performance of CRAID, there are two behaviors that we need to distinguish, depending on the effectiveness of the prediction algorithm. For the 7 traces that we simulated, in 6 out of 7 traces, we found the behavior similar to what we're seeing on the left side for the web users trace. The performance for read requests is similar to those of an ideal RAID 5 and is always better than that of the extended RAID 5, even in those cases when we are using an extended RAID 5 for the archive partition. And increasing the cache partition size helps to reduce the response time of the requests. Nevertheless, for the project trace, we found out that all the response times were higher in CRAID, even higher than those for the extended RAID 5. The reason for this, after examination of our results, was that the hit ratio, well, the effectiveness of the prediction algorithm for the project trace was worse than for the other traces. The hit ratio was lower, and also the eviction count was higher, which added more bootkeeping requests that interfered with normal user operation. Now, if we compare the results of CRAID against that of the dedicated SSD caches, the first thing that we can see is that the dedicated SSD outperforms CRAID. This is to be expected due to the difference in performance of the two types of devices, but we can also see that for some cache size configurations, the performance of CRAID is slightly better than that of a dedicated cache of SSDs. This benefit of performance comes from the increased sequentiality of data access and the improved data locality. For write requests, there is only one behavior, and CRAID usually always behaves better than the extended RAID 5 and usually has performance times close to that of an ideally redistributed RAID, and in some cases even better. When compared to SSDs, for some of the traces, we show the same behavior that we have seen before, and the dedicated cache outperforms CRAID, but in some cases the write requests are slower than those of CRAID. After examination of our results, we found out that the SSDs were using, had more pending requests and were using less concurrent disks than the alternative on CRAID. This is to be expected since we are only using 5 SSDs. Now, for the workload distribution, in this experiment, we measured for each second of simulation the coefficient of variation from an ideally redistributed workload. And we computed the cumulative distribution function in order to see how the overall simulation behaved. One way to interpret these figures is that all the if the curve is located to the right, the workload is more deviated. Well, the overall workload is, for each second is more deviated from an ideal distribution that if it's located to the left. We can see that the segmented, the extended RAID 5 Plus has a significantly worse workload distribution than the ideal RAID 5, which is expected. But interestingly, in some traces, in most of the traces, we found out that CRAID has a similar workload distribution than that of an ideal RAID 5, and in some cases, it is significantly better. When compared to the SSDs, expectedly, the workload distribution of the SSDs is worse because we're using less devices than we're using for CRAID, when we are using all the available devices in the RAID. Now, to conclude, we have seen that CRAID offers a lower grade overhead with increased locality and sequentiality of hot data, which leads to improved read and write performance. It also has shown good workload distribution that is close to that of an ideally redistributed RAID, even in the cases when we were using a segmented RAID as an archive partition. All the results that we have shown here were using more or less 1%, around 1% or less of the available capacity in the RAID, which is acceptable. And finally, even though SSDs outperform our results, CRAID could be an alternative when you have to take into account your budget, since you can implement it with your already available disks. And in principle, the strategy should also work with full SSD RAIDs. As a future work, we plan to abandon simulations and work in a fully fledged hardware prototype. CRAID currently supports RAID 0 and RAID 5, and we plan on working on extending it to RAID 6 and more general Azure coding support. And we would also like to explore smarter prediction or rebalancing algorithms, since the ones that we are using now are really simple, that could take advantage or more complex relationship between the hot blocks. Finally, we also want to extend it beyond RAID storage, maybe to tiered storage, or even to object-based storage with randomized data distributions. With this concludes my presentation. If you have any question, I'll be glad to answer it.
Okay, well, I'll go. One of the more challenging parts of this work is finding traces that represent a wide variety of what you're going to see. Can you comment on what the characteristics of the traces were that impact your rebalancing algorithms?
Well, we tried to find all the publicly available traces that we could find. Unfortunately, we weren't able to find many, and we weren't able to find traces, for example, from cloud workloads or more recent server workloads. Basically, the traces that we are using for the paper are file server workloads, or I think a server and a web server, and an email server. Right now, I can't recall anything else. Okay, thank you very much.